Hello, this is Bob Schmidt again in our continuing series on QC optimization, or the war on variation. This is one of a series of videos that are designed to provide a common language and understanding of quality control. And the objective of this video is to help you understand the concept of stability. As you'll recall from the introductory video, stability is one of three concepts that are fundamental to quality control. We will focus on stability in this video, and we'll cover capability and controllability in videos to follow. Let's start with the process behavior chart. You may know this as a Levy-Jennings chart, but that's a useless name because it isn't descriptive. These charts should be called process behavior charts because that's exactly what they describe. Also, a Levy-Jennings chart refers to a particular type of process behavior chart. A Levy-Jennings chart refers to a process behavior chart where each point represents a single measurement. However, we can track all kinds of things. We might track an average of several values, ranges, differences between subsequent measurements, and various other statistics. All of these types of charts are process behavior charts, but they are not Levy-Jennings charts. So there's potential for confusion because it's likely we'll start using a variety of different types of charts in this project. So from now on, let's agree to call these process behavior charts. As the name implies, these charts are used to investigate process behavior. And more precisely, the process behavior chart is used to evaluate whether a process is stable. We'll get to that, but before we do, we need to cover a few preliminaries. The process behavior chart shows the results for a sample with a known value or control that is repeatedly measured over time. Concentration is on the vertical axis and time is on the horizontal axis. In this chart, the control has a target of 10 nanograms per mil, but we see that the measurements vary around the target value over time. We use this chart to determine whether the process is behaving quote-unquote normally. Thus, we look for some unusual pattern in the results, and if we see one, we suspect there's a problem, and that is that the process is unstable. Thus, to use a control chart effectively, you need to be a student of variation and need to understand what causes variation in process behavior. Why do measurements vary over time? To answer that, we need to think of our QC result as the output of a measurement system. The measurement system produces a result, which we can plot over time on the process behavior chart. To understand the variation in the output, we have to understand how the measurement system works. The measurement system has many inputs. And the system takes all these inputs, and these are somehow combined to produce the output. And in general, there'll be lots of inputs, and the value of the inputs determine the level of the output. The inputs could be things like mixing time, the temperature, the age of the reagent, dust levels, voltage in the line, age of the detector, and so on. And in general, we don't even know all of the inputs. And here I show a system with 137 inputs, just for an example. This sounds crazy, but in fact, maybe the number of factors that affect the output. The point is, there's many inputs. Not only do we have many inputs, but they vary over time. Here I've added process behavior charts for the inputs to the slide. We see different patterns of variation for each input. The top input has a random pattern centered about a single value. And the middle input has a random off and on pattern. And this might represent whether a specific step in the SOP was followed or not. The last input has two types of variation. On the left, the values vary around one set point, but halfway through, there's a shift and there's variation around a new set point. The output of our system varies because there's variation in the inputs. And if the inputs were constant, there'd be no variation in the output, and we wouldn't need to worry about quality control. But inputs do vary, and this in turn causes variation in the output. Each input can have a different impact on the output. On this slide, the variable on the left has a significant impact on the output, whereas the input on the right has very little impact. So we have inputs that vary over time, and each input can have a different association with the output. And the point is that inputs are not created equal. Some inputs matter and some don't. Moving back to our system diagram, we show the effect of a high impact input. We see a step change in the input variable that corresponds to a step change in the output. There are a vast number of possible relationships between an input and the output, and it's important to develop an understanding of these relationships for each of the inputs. This allows us to reason backwards from patterns in the output to patterns in the input and to control the process. We call this process knowledge, and this process knowledge is critically important for effective quality control. Variation in output that can be associated with the variation in inputs is called assignable cause variation, because the variation can be traced back to a change in the input. The change in input on the left caused the change in the output on the right. Therefore, when we see a change in a process behavior chart like the one on the right, we can reason that it may have been caused by a change in input similar to that seen here. An assignable cause creates a pattern in the output that can be detected. Here we see a shift. This pattern alerts us to a problem in the input that we can potentially identify. We can assign the cause of the shift to some change in the input, so we call it an assignable cause. Assignable cause variation is one of the most important concepts in quality control. We can prove the causal relationship by conducting an experiment. We can control the input variation, and if this reduces the variation on the right, we can be pretty confident that this was the cause. We can assign the shift in the input as the cause of the shift in the output. It takes observation, experimentation, and sometimes statistical analysis to understand these relationships. Eventually, these investigations lead to process knowledge, which in turn enables us to control output variation. So going back to our system diagram, we see that the system has lots of inputs. In fact, here we have 137. Nobody's ever going to be able to understand how each of these 137 inputs affects the output. This is clearly impossible. So what are we going to do? Well, as we stated earlier, not all inputs are created equal. In general, only a handful of inputs will have high impact. And this is good news because it enables us to focus on just a few input variables. And we call these inputs the vital few. The slide shows the relative impact of a large number of inputs. The vital few are indicated in red. You can see that they have the larger impacts. And we can understand the impact of these variables, and they will be assignable causes. We refer to the other variables, those in blue, as the trivial many. We probably won't even know about many of these inputs, let alone how they affect the output. So we focus on the vital few. Obviously, the dividing line between the vital few and trivial many is arbitrary and could change with time. You may discover more assignable causes as you gain more knowledge, but the general principles remain the same. Focus on the vital few. So what do we gain by grouping these inputs into two categories, the vital few and trivial many? How does this help us? The answer is that we design controls to reduce the variation in the potential assignable causes or high impact inputs. This means we have two kinds of inputs: controlled inputs and uncontrolled inputs. When the vital few high impact inputs are controlled, all the variation in the output is due to variation in the uncontrolled inputs, or the trivial many. Recall that assignable cause variation causes a detectable pattern in the output. And when these inputs are controlled, there's no pattern at all in the output. When assignable cause is present, you'll see a pattern, and we can potentially link the pattern in the output to a cause. When assignable cause variation is controlled, that is, all the high impact inputs are controlled, there's no detectable pattern in the output. We have no way of linking the output to a cause. We can't tell why one point is higher than another, or why there were two in a row that were on one side of the center line, or something like this. We might refer to this variation, when all the assignable cause variation is controlled, as residual variation. So how do we use this to achieve process control? Controlling a process involves identifying and eliminating sources of variation. When these vital few high impact inputs are controlled, the variation in the output will be controlled. This requires a profound knowledge about the process. This is gained over time by experimentation and observation, and the process behavior chart is the key tool for gaining this knowledge. So let's take a broad view of how we control a process. We monitor process behavior for signals that suggest an assignable cause. So remember, when there's assignable cause present, there'll be some sort of detectable pattern in the output, and here we see a step change. There are many different ways of monitoring process behavior. You may have heard about Westgard rules, and Westgard rules are one method of monitoring a process for signals for an assignable cause. When a signal is detected, we apply our process knowledge to eliminate that cause. Process monitoring is designed to detect patterns that result from assignable causes. Once we detect such a signal, we start an investigation to identify and eliminate the cause. We can do this efficiently by having a plan that is triggered by different types of signals. This is called an out-of-control action plan, or OCAP. In essence, an OCAP is a flowchart that directs us to the most likely cause based on the type of signal that was detected. The OCAP is based on process knowledge gained from experimentation, observation, and statistical analysis. One can also use techniques such as process flow mapping and failure modes and effects analysis to identify ways in which the process can fail and predict how those failures would manifest themselves in a process behavior chart. The Toxicology and Trace Elements Lab use OCAPs very effectively. They were able to reduce the time to identify and control an assignable cause from hours to minutes. They doubled the capacity of their laboratory with existing equipment. QC optimization has two objectives. First, to control the inputs so that failures occur less frequently. And second, when failures do occur, to identify the cause and restore control quickly. This results in much less wasted time. The objective of the QC optimization project is to develop this capability across the company. Our team is here to help you do this. We will teach you this process on a few starter projects, and once you've learned the basics, you should be able to go forward and lead your own improvement projects in your laboratory. The QC optimization team will be available to provide advice and assistance as you go forward. It's important to note that systems are composed of subsystems. When controlling a process, you will find that an input, for example, x1 in this diagram, is the output of another system. Thus, to control the variation in x1, we need to control the inputs which determine the variation in x1. These are x11 and x12 in the diagram above. This is a general principle in quality control, to look upstream for control points. This way you can prevent failures rather than simply detect failures in the end result. At the end, it's too late and you've invested time and money in producing a defective result. It is much better to control upstream inputs before they affect the final result. The previous slide introduced the principle of looking upstream. And the further we move upstream, the less time and money has been invested in the final result. So by looking upstream, we can potentially identify errors at a point where there's been little investment and before there's any impact on the final result. Moving upstream is therefore a cost-effective way of reducing errors. This brings up a useful point regarding terminology. This is the difference between process control and product control. Product control involves inspecting the final result and determining whether it is acceptable. Process control involves looking upstream, identifying and controlling assignable causes. In product control, we inspect quality in. We examine each run and throw out the faulty ones. By doing this, we retain good results and achieve high quality. But is this really good quality? In a high quality process, we would ensure that the output of each subsystem was acceptable by controlling the inputs to the subsystem. Inspection is an expensive and largely discredited method of achieving acceptable results. Instead, we should build quality in using process control. One of our objectives is to help the labs use process control rather than product control to achieve reliable results. So what does a process behavior chart look like when a process is controlled? Remember, the process is controlled when we have removed all assignable causes of variation by identifying and controlling the high impact inputs, the vital few. The remaining variation is called common cause variation. You might think of it as residual variation. Common cause variation is characterized by the fact that it contains no information. We have no idea why one point is different than another. If we could say why one point was higher than another, we would have identified assignable cause and could control it and eliminate that factor. Such a process that exhibits no patterns is said to be in statistical control. A process in statistical control is stable and reliable and has natural variation that is predictable. We call this predictable variation the voice of the process because it represents the best achievable performance with respect to variation that the process can achieve. When a process is in control, it is operating as designed. The variability can't be reduced without substantial redesign of the process. This natural variation is a key input to a control process. The standard deviation of the natural variation is used to design a quality control plan. It is vitally important to use data that only contains common cause variation to determine the standard deviation of your process. The observed standard deviation should only be measured after you have removed all assignable cause variation. You can't do effective quality control if you don't appreciate the difference between these sources of variation. If present, assignable cause variation will inflate your estimates of natural variation and make your quality control ineffective. So what's the big deal about stability? Why do we emphasize this so much? Well, first of all, we want a stable, predictable process, and this is obviously a good thing. But it's also very important to have a good estimate of the process variation. If we're going to have a war with variation, we need to understand the size of the variation, and we can only do this if the variation is stable. So in the upper panel, we see an unstable process. And the variation, if we measured it here, is not really meaningful. In the bottom panel, we see a stable process, and the variation is meaningful. So just from an operational perspective, it's good to have stability, and from the design of a control system, we need to have a good estimate of the variation, and that's only can occur with a stable process. Let's take a step back and look at the big picture to see how the things we have just covered fit in the overall system. Starting at the left, a stable process enables us to estimate the variation. And as the diagram shows, this is used in two ways. First, process variation is used to assess process capability. And we can only evaluate capability when the process is stable. And capability is a performance measure that's used to assess risk to patients. Second, the variability is used to determine the size of errors that we can detect when the process does go out of control. And this is called power analysis. Power is the ability to detect a change when it occurs. And the power depends both on the QC plan we select and the size of the variation. So you can see that the variation from the stable process feeds into the power analysis on the diagram. Controllability, to the right, is about reducing the risk of reporting unacceptable results when the process is out of control. Say the process does go out of control. Our ability to detect it depends on the size of the error that we can detect, and this comes from the power curve, which we described in an upcoming video. The power curve depends on the QC plan and the process variation. The process capability tells the size of errors we need to detect to prevent reporting unacceptable results. Obviously, big errors are easier to detect than small errors. And a capable process only requires you to detect big errors. So designing a QC program is about selecting a plan that can detect the errors you need to detect at reasonable cost. Note that control is relatively easy when the process is capable. A process is capable when the variation is low. We can select a less costly QC plan when the process is capable, and therefore we want low variation. And this brings us to the last piece, process improvement. We want to make changes to the process to reduce variation. And when we do this, it starts the whole process over, and we can reevaluate the QC plan, probably choose a less costly QC plan, and reduce risk to patients. We'll talk about all this in detail in future videos, but for now, this is just a preview of where we're headed. The previous diagram showed a bird's eye view of the quality control process. Not to beat a dead horse, but it relies on three concepts: stability, capability, and controllability. Okay, let's summarize what we've gone over. First, we talked about stability and how it's related to variation. In particular, we talked about the concepts of assignable and common cause variation. We then talked about how to establish control by identifying and removing assignable cause variation. And lastly, we talked about the idea of product versus process control and the importance of looking upstream for errors. Well, that's it for this video. I hope you found this useful, and please contact me if you have any questions or would like to talk about anything I presented. And thank you for listening.